charges moving in magnetic fields. We've learned from experiments that there is a force acting on the charge when it's traveling through a magnetic field. What we know is that the magnitude of that force depends on the magnitude of the charge, the speed of the charge, the strength of the magnetic field, and sometimes some people forget on the angle between velocity and the field. So here, even if the charge is moving in the field, it might be force equal to 0 if velocity is parallel to the field. In that case, the angle is 0, sine of 0 is 0, or velocity is anti-parallel to the field. In that case, the angle theta equals 180 degrees, the sine of 180 is 0. Again, so all four variables should give some non-zero values: charge, speed, field, angle. Easier to carry on calculations with this expression. Here we can see that only that component of velocity which is perpendicular to the field is important. If velocity doesn't have a perpendicular component, there is no force. Now, we can use this fact to answer this question quickly. So actual velocity is shown by a green arrow, and the red arrow represents the component of the velocity perpendicular to the magnetic field. And the larger component is, the stronger the force for the same particle in the same field. This is how the force depends on the angle. So if you want to rank these forces in terms of magnitude from largest to smallest, that would be the ranking. Largest perpendicular component gives you the largest force. No component at all, no force at all. So that's the question about ranking magnitude of the magnetic force acting on a particle moving in a magnetic field. So now read this question, please. Now, a magnetic field is presented, and electric field is presented. And we have to rank particles, well, the same particles, same magnitude of the charge in the same magnetic field. We have to rank from largest to smallest magnitude of magnetic force acting on it. Okay? So that's our first question, just to test the system. So, folks, read the question carefully and choose your answer you think fits the best. I probably should move the timer a little bit so you could see all. Oh no, that's not the component, that's electric field. So a red arrow represents electric field in this picture. And we have 5 options. What's yours? 5. So basically you're ignoring the presence of electric field. That's correct, that's what you're supposed to do. Because the question is not about the net force or total force. The question again is about magnetic force. So if the question is about magnetic force, it doesn't matter how many other forces acting on a particle. Magnetic force depends on Q, B, V, and sine. if we had to answer a question related to a net force acting on this particle, in that case the picture would be different. We would have to encounter for electric field as well. But you're absolutely right. If we read the question, and the question is rank in terms of magnetic force only, the ranking stays the same. All right. Now, the right-hand rule gives us the way to relate three directions. The direction number one is the component of velocity perpendicular to the magnetic field, not velocity itself. Because if you have magnetic field like this and velocity like that, the velocity has two components. The component which is parallel to the field doesn't do anything. Only the component which is perpendicular to the field is involved in the magnitude of the force. So one direction represents the component of the velocity perpendicular to the field. We use it in this finger for that. And these three fingers represent magnetic field lines, and the thumb represents the force. So if we know any two directions out of these three, we can figure out the direction of the third one. And all we have to do is just apply this rule several times just to practice. So, first question. These circles with little crosses represent magnetic field directed into the screen. And this charge doesn't move. So, what is your answer about the direction of the magnetic force acting on this charge? There is no good place for the timer. Magnetic field is uniform. It means it has exactly the same magnitude and direction everywhere, which is normally the case. The charge is positive, not negative. So if we want to relate three directions, we have to use right hand, our right hand. And of course, we have to keep in mind the expression for the magnitude of the force just in case. And here, the most popular answer is wrong. Remember, I stressed once that we have to be, when we read a problem, we have to be looking for most important words and less important words. Here, in this situation, there is one word which is the most important, which is what? What word is that? Stationary. What does it mean? No velocity, it doesn't move. If there is no velocity, it doesn't matter how strong the charge is, how strong the field is, the magnitude of the force must be equal to zero, because you're multiplying by zero velocity. So in this situation, the right answer is number 8. The force is zero. Now, the same particle, same magnetic field, the particle is moving now. So the magnetic field points into the screen, and the velocity of the particle is out of the screen. The same question, same options to answer. Same time to answer. Same two facts to use. The magnitude of the velocity, number 1. The right-hand rule, number 2. you have to ask yourself, okay, does the particle have a charge? Does magnetic field, well, surround the particle, presented in the region? Is the particle moving? What is the angle? These are four variables directly related to the force acting on the particle in a magnetic field. So this particle has a charge and it's positive. So we can use the right hand if we need. The magnetic field is presented. The velocity, yes, it's moving. The last variable is the angle. Magnetic field points into the screen, well, velocity points out of the screen. The angle between two arrows is equal to what? 180. Sine of 180, 0. There's no force acting on this particle. The velocity doesn't have a component perpendicular to the field. So in this situation, the right answer again is 0 force. Well, finally, actual question. An actual question. There is a particle, it's moving in the magnetic field. This is a snapshot. Of course, in a fraction of a second, the velocity changes. We'll talk about it later, very soon. This is a snapshot. That's what's happening now. So the question is, what is the direction of the force acting on this particle from magnetic field now? Does it have a charge? Yes, it does. Do we see magnetic field? Yes. Is velocity perpendicular? Well, parallel or anti-parallel? No. Perpendicular? No, but it doesn't matter. It has a component which is perpendicular to field. So the magnetic force is not 0 anymore, and it points in some direction, which is, well, you'll tell me right now. Remember, again, I mentioned several times that thinking is not very much involved in physics, as, for example, drawing, or, in this case, moving your hands. I don't see many people moving your hands. A question like that cannot be solved without actually trying to do something with your hands. Of course, if you have a really good visual imagination, that helps, but I don't. For example, I have to use my hands, I have to draw pictures to answer questions like that. Six. Let's see what 6 means. Out of the 50. All right. So, in this situation, we take our hand. Well, fingers supposed to be directed in the direction of the magnetic field. Well, this is the velocity. The component which is perpendicular to field points like that. So the thumb shows the direction of the force out of the screen. So, which is the correct answer. To show, well, we have to use three-dimensional pictures. So if we want to show an arrow pointing out of the screen, we use a little circle with a dot inside. So a little circle with a cross inside represents an arrow pointing into the screen, and with a dot out of the screen. Well, a negative charge. What do we do now? I want to change the question. I want to ask you, for a negative charge, which hand would you want to use? 1 for the right hand, 2 for the left hand, 3 for your friend's hand. 1, press 1 if you want to use the right hand, press 2 if you want to use your left hand. Any other button if you don't know what to do. And I'm not going to give you much time for that. Well, 12% out of 25, it's about 6, would use friend's hand, which is fine if your friend actually fine with that. Now, technically you could use any. You just have to remember for the negative charge, if you're using your right hand, you have to reverse your final answer. Or you can just use your left hand directly. And in this situation, so what do? Magnetic field lines point out of the screen. So I cannot use my index finger for that direction. I have to use these fingers for this direction. Now I have to point my index finger in direction of velocity. So it's kind of hard, but it's doable. And the thumb shows the direction of the force now acting on this charge, traveling in magnetic field. It could be an electron. Well, and one more question. Now what we know is the force and the field. This black circle with a cross represents the force directed into the screen. I'm going to start collecting your images. And these arrows represent magnetic field. So, force, field. Something like that. When we talk about velocity, force, field, we always keep in mind this kind of a situation. Basically, it's XYZ axis. XYZ axis have the same orientation as velocity, field, force. So XYZ equals VBF. And in your PY105 course, you've studied similar situations. For example, radius vector, force and torque, or radius vector, velocity and angular velocity. Here, we just have to remember definitions. We know that one arrow must represent the force. We know that that one arrow must represent magnetic field. And we know that another arrow must represent what? Velocity. That's a common misconception. The component of the velocity, which is perpendicular to the field. So, in this situation, what you can find out is the direction of the component of the velocity perpendicular to the field only. So, well, field lines, force. So this arrow represents the component of velocity perpendicular to the field. However, if we know only one component, it doesn't give us the whole information about velocity. Velocity could be actually any of those arrows. They all have the same perpendicular component. So, when we know for sure direction of velocity and field, we can figure out the direction of the force. When we know the direction of velocity and force, we can figure out the direction of the component of the magnetic field perpendicular to the velocity. And when we know the direction of the field and force, we can figure out the direction of component of the velocity perpendicular to the field. All right. Which particle is positive, which particle is negative? That's another application of the right-hand rule. We know that right hand directly represents connection between velocity, field, and force. If we cannot use the right-hand rule for a specific particle, it's not a positive charge, it must be a negative charge. So here, I don't want to ask you this question, let's just think through. The particle number 1. So first of all, in order for this particle to move like it's shown, this is the trajectory of this particle, the force acting on this particle here must point straight up. That's what makes it curve. Well, it's a counterclockwise motion. So, and here, at the point where the particle is entering the field, the velocity of this particle, of V1, F1, points to the right. And only now, after we have drawn these arrows, we can figure out the rest. So magnetic field points into the screen. The velocity points to the right. The thumb is supposed to show the direction of the force, and the force also points up at the time, so the thumb points. So the right-hand rule works for a particle, number one. What about number 2 or 3? The answer for 2 and 3 is supposed to be the same because the curvature is the same for both. So, again, particle number 2 is entering here. That's initial velocity. It changes over time, but at this point it's not important. And the force acting on this particle points down. So, field, velocity, force. The thumb points up, actual direction of the force is down. So the right-hand rule doesn't work for the particle number 2. It must be a negative particle. Any question? If we would use left hand, that would perfectly work. Velocity, field, force. Left hand works for number 2 and number 3 particles, so they are both negative. Electron, like probably. Now, here, it's a really good question. We have electric field acting on the particle. So these arrows represent electric field now. What's supposed to be the direction of the force acting on this particle from electric field? Well, the force acting on the particle from electric field is related to electric field like this. All we need to know is the charge. If the charge is positive, force has the same direction as electric field has. And if the charge is negative, the force is opposite to the field. We look at the picture, the charge is negative. So, if the field points into the screen, the force points out. In this situation, this force, electric force, is not related to velocity at all. It's related to the charge and the field only. Very good question. Well, this is one of the handouts. You should have it, but just in case I brought some more, please use it to answer this question. What is happening? This particle, which is a proton, what do we know about the proton? It's a positive charge. Traveling plus. It's a proton plus traveling in this direction. That's velocity. What's important, the velocity doesn't change. Constant velocity. What does it mean? Constant velocity means something about something. There is no acceleration. Acceleration is 0. What does that mean? No acceleration, no what? Which force? Gravity? Magnetic? Net force. There is no net force. Net force is 0. So, here, two fields are acting on a particle. Magnetic, which we see, and the direction of the magnetic field is into the screen. An electric field, which we do not see. Our goal is to figure out the direction of that electric field. So the particle would be moving with constant velocity. So I'm going to give you a minute to think about it and choose your answer. Of course, it's about drawing a three-body diagram. Because if you have two forces acting and net force is electric force must have the same magnitude and opposite direction as magnetic force has. So first you have to draw. And to do that, you can use your right-hand rule. And it has to be an arrow representing that force. You cannot do it without an arrow. Because only after making this step, you can draw another arrow representing force acting on a particle from electric field. And now, if you know the force acting on a particle from electric field, and you know the charge of a particle, you can figure out the direction of the field. This is a sequence of thoughts or drawings should be done to answer this question. So, proton, magnetic field, velocity. So, velocity field, the magnetic force points straight up. That magnetic force, F(V). To compensate this force, electric force must point straight down, F(E). It has to be equal to charge times field. For the positive charge, the direction of the field, the same as the direction of the force, which is down. So we have to apply electric field down in order to make this particle traveling with constant velocity. If we turn off electric field, what's going to be happening? That's the next question we're going to talk about. Well, we're going to talk about particles traveling in a uniform magnetic field. In a uniform magnetic field, which would be a field between the poles of a large magnet. In a uniform magnetic field, particles travel in circles. And sometimes we actually have to make our mind around to see that circle. This picture represents, well, let's say a positive charge travel entering magnetic field in this direction. So this is a snapshot of what's happening now. Magnetic field points to the right, and we need to answer this question. To answer this question, we have to put yourself in the shoes of the observer, and that observer might be looking at this picture like this, from the direction of positive x-axis, or like that, from the direction of positive y-axis, or like this, from the direction of positive z-axis. Well, technically, also three more directions possible: negative x, negative y, negative z. And only if you look, well, from one of these directions given to you, you can see a circle made of a trajectory of a particle, and that circular motion happening either clockwise or counterclockwise relative to that specific observer. So, in this situation, how will you answer this question? what will be happening to this particle next? Okay. Well, of course, at first we need to figure out the shape of the trajectory and then try to turn around it in your mind. And then choose correct answer. So here, what we know for sure at first is that at that particular instant, velocity, magnetic field lines, force points out of the screen. So if velocity points down and the force points out of the screen, to see both vectors, you would have to look at it, well, along the x-axis. So your point of view to answer this question is supposed to be from positive x direction. So you will see both arrows, velocity and force. If you're looking like this, from negative y direction, for example, you do not see this force, which is not very good. In this direction, two arrows, two vectors, always form a plane, and the motion of the particle happens in this plane. In which direction? Well, the force makes trajectory being curved like this, so it's supposed to be the direction like that. If we're looking at this circular motion from a positive x direction relative to us, that's going to be a counterclockwise motion. And there are many questions like that when you have to, visualize the situation from one direction or another direction. And what do we know about circular motion? Like this. So that's a rhetorical question. We know everything about circular motion. We've studied. So we know that when a particle moving in a circle with constant velocity, there's acceleration. What's the name of that acceleration? Centrifugal acceleration, because it always points to the center. And if you want to answer this question, particle is moving with constant velocity, constant speed, what would be your choice? Speed. Because velocity also has a direction, and direction constantly changes. For example, here, and you're supposed to do it if you need, the magnetic field line is now pointing out of the screen like this. The velocity of the particle points down, and now, again, velocity, field, force points, which is the left. Force equals ma. A equals change the velocity over time. So, force, the direction of the force represents the direction of the change of velocity. That's important. So, if the force points to the left, change in the velocity points to the left. The next velocity in a fraction of a second is going to be equal to the original velocity plus new velocity, which is this arrow, v2. So velocity constantly changes. However, force always is perpendicular to velocity. That means, well, first of all, particle is traveling. It's been here, now it's here. The new velocity points like that. The new force now points like this. And the particle now is traveling to new location, new velocity, new force, new location, new velocity, new force, etc., etc. That's why it's traveling in a circle. So velocity changes, but speed stays the same. And all we need to do now is just apply Newton's second law, expression for centripetal acceleration, and sometimes, well, for kinetic energy, for the period, and for the magnetic force to answer all possible questions. For example, here, if we solve these equations, we can calculate the radius of that circle the particle makes. It depends on 4 variables: mass, speed, magnitude of the charge, magnitude of the field. So if we have 2 different particles traveling in the same magnetic field, the particle with the larger radius, well, we cannot answer this question because there are more variables involved. We need to know more specifically something about charge or speed to relate all those variables. And sometimes with additional information we can. For example, if we have the same particles, 2 protons traveling in the same magnetic field. In that case, M is the same for both. Charge is the same, field is the same. In that case, for 2 equal particles, the radius and speed directly related. And in that case, faster particle travels in the larger circle, or larger circle represents the particle traveling faster. And of course, with this circular motion, we can introduce a physical variable, a period, how much time it takes to make one whole circle. To calculate the period, we need to do this. We just have to calculate this ratio, distance traveled, which is equivalent divided by speed. Turns out the period depends only on 3 variables: the mass, the charge, and the field. So, 2 equal particles, 2 protons, for example, traveling in the same magnetic field must have the same period because they have the same F, the same Q, the same B, and the period doesn't depend on velocity. Of course, one particle might make a large circle and another might make a smaller circle. And there is a similar question related to kinetic energy. Well, in that case, you will have to apply an additional equation. Here, what is happening? We are ranking these 3 particles in terms of speeds. Well, we just said when particles have the same mass and charge, radius directly related to speed, larger radius, faster particle. So we would have to answer this. Now, and of course we can rank those particles in terms of forces. Same particles, same M, same Q. In this situation, if you apply the expression for the magnetic force, force is directly related to speed. More speed, more force. And if you want to rank them in terms of the period, we will have to answer none of the above, because for these particles, because they have the same mass and charge and the same magnetic field, the period must be the same. Well, I have one more handout, this one. I'm just going to start to show how you can approach a problem like that. Basically, the easiest way is actually organizing all your data in terms of some kind of a chart or table. So, what do you know? Or what you don't know? Well, in this problem, you have 3 particles involved. A, B, C. And for each particle, there is some mass, there is some charge, there is some speed, force acting on the radius of the trajectory, period of the motion, and kinetic energy. What sometimes some students confuse is, for example, this letter M and this letter M. This letter M is just an abstract placeholder for the mass of a particle. So for example, for the particle A, the mass is equal to 4m. For the particle B, the mass is 4m. And for the particle C, well, it's an unknown variable. Same is true for the charge. This Q is just a placeholder. It represents some charge of a particle. But for different particles, it could be different charge. Again, for the particle A, the charge equals 2Q. For B, well, it's an unknown. For C, it's Q. Speed, V. V, 4V. What do we know about radius? Well, this is the radius for particle A, let's say R. The same is going to be the radius for particle B. But for the particle C, the radius in this case is going to be 2R, because it's twice larger. And now we can use these equations step by step to figure out all, okay, that's the radius, that's the force. To figure out all empty cells, to compare different variables for different particles. So after we just finished plugging in all the values in all the equations, here everything we know, and these are the equations. This is what we get. And again, at that step, we don't really have to think about anything. We just take a value, plug it in equations, and write down the results. And here, instead of question marks, we have introduced two specific unknowns, number x, number y. These are the numbers, because now all the masses are written in terms of m, all the charges in terms of q, and you could have maybe a similar problem with unknown speed. In that case, your unknown speed would be written like z times v, and what we're looking for is just these coefficients, x and y. X, of course, is a positive number because the mass is never negative. This number, y, could be both positive and negative, so we'll have to figure it out. After finishing this table, now we have to start thinking a little bit. We have to find some connections, and to do that we could use different equations. For example, another equation for the force. Well, first of all, if you look at this expression and that expression, well, they represent different forces, technically. This is the force acting on a moving particle from magnetic field. This is the force acting on a particle or any object making circular motion. Well, of course, if we have only one particle, only one force, in this problem, this is the same force, which is good. Well, if we look at this expression, we have to state that any two particles with same mass, speed, and radius must have the same force acting on them. Do we have any two particles with same mass, speed, and radius? Yes, we do. A and Z, the same mass, the same speed, the same radius. Which means they must experience the same force acting from magnetic field. So this expression and that expression must be equal to each other. That immediately gives the magnitude of this coefficient, the absolute value of y equals 2. And there's another way to calculate the same value. We could again, instead of comparing forces, we would compare periods. Well, how do we calculate the period in general? Distance over time. So if we look at these expressions, we can say again, two particles with same radius and same speed must have same period. So in this situation, again, particles A and B have the same t, the same period. So we could compare these two expressions. This expression has to be equal to this. And that, of course, gives exactly the same result for the magnitude of y2. And now if we want to answer the question, is it a positive number or a negative number, we just have to look at the picture. We know particle A is positive, and it's traveling clockwise. That means all other particles traveling clockwise must be positive, and all particles traveling counterclockwise must be negative. So this particle C also is positive, clockwise motion. Particle B makes counterclockwise motion, it has to be negative. So that's why this charge actually has the value -2q. Any questions? Well, of course, we can figure out the direction of the field. We just have to apply the right-hand rule, for example, to particle C. It's entering the field in this direction, that's B, C. And because the trajectory curves down, that means here, at the entering point, the force acting on it points right down. And we know it's positive. So, velocity, force, sometimes you have to almost break your hand. Magnetic field points up. Well, with this kind of approach, you can solve any problem related to particles traveling in magnetic field. Now we can talk about possible applications. One of these applications is this. This. Cyclotron. It's a first particle accelerator. So if you have a charged particle, what you can do, you can apply potential difference between these two halves of the circle. So here, electric field accelerates the particle, but magnetic field, which is, well, perpendicular to the screen, makes this particle moving back in this spacing. So electric field again accelerates, the particle moves faster and faster and faster. And now, today, well, we use a similar idea. Just instead of this simple device, people have spent billions of dollars to build up a hadron collider in Switzerland, and now all of our stuff here, the faculty spends half of the time in Switzerland, which is good, I guess. Now, another situation might be happening when a particle has velocity which is not entirely perpendicular to the field. Let's say that's magnetic field, and let's say this is the velocity. What should be happening? Well, velocity has two components. Only perpendicular component is important in terms of forces acting on the particle. So because of the perpendicular component, particles start circulating. What does parallel component do? Nothing, it just keeps moving particle in the same direction. So in this situation, particle makes two motions simultaneously. Like this. It makes a circular motion, and at the same time it keeps traveling parallel to magnetic field. So if we combine these two motions, what we get is spiral motion. Well, another application of this theory is the mass spectrometer. Mass spectrometer is a device which we use to measure masses of particles. It has three parts. First of all, we have to accelerate the particle. To do that, we apply electric field. Like here, two parallel plates, big capacitor, electric field accelerates particles, and if we apply law of conservation of energy, we can calculate the kinetic energy of the particle when it leaves the electric field. Now, we don't need all particles. Remember, mass, charge related to speed. So we need to know exactly the speed of a particle. To do that, we use so-called velocity selector. Velocity selector is a region where two fields are active on a particle, electric and magnetic. And on Wednesday, we had a problem similar to this. Two fields, however, a particle doesn't have any acceleration, net force equals zero, it's traveling with constant velocity. How could it happen? Well, in order to that happen, forces must have the same magnitude. When forces have the same magnitude, that gives us a specific relationship between electric field and magnetic field. And since we are manipulating with field, we can set up E and B in such a way so only particles with this particular speed getting through this velocity selector. What is happening if velocity is higher or lower, if particle moves faster or lower? Well, this is my first question. Let's say positive ions traveling faster than the speed we're expecting. So in that case, what's going to be the trajectory of those particles look like? The deflection should be happening up or down. Alright. That's supposed to be channel 41. It worked in the morning. It still works. So, if you look at the picture, this arrow represents the magnetic force for magnetic field acting on the particle. This arrow represents electric force. In the picture, they cancel each other out, so the net force is zero. Why? Because this particle has the exact right velocity. The question is about a different particle, which entering this region faster than this one. So, if it travels faster, what's supposed to happen to well, I would like to know what that person who pressed 5 thought when did it. There's no answer like that. If you're using clickers just to get the attendance, it doesn't worth it. You should try to think through a problem and you should try to find the right answer. Because trying, it's like exercising, like bodybuilding. Brain building works in a similar way. It starts working better and better only when you exercise it more often. It's just a fact. So here, we know that this force, which is equal to charge times field, is not related to the velocity at all. So by changing the velocity, we do not change electric force. Only this force has the magnitude related to velocity. So, if we change the velocity, if we increase the speed of the particle when it's entering this region, we're going to have to increase the force acting on the particle from magnetic field. So in this case, net force is not zero anymore. There is net force pointing up, and the trajectory should go this way. So, wrong, wrong. I actually have a picture of what's happening. Well, it's just traveling, so it's not very interesting, but it's speeding up. When it leaves the electric field, it goes through this velocity selector. When the velocity is just right, there is no deflection. So, if it's too fast, magnetic force wins over electric force. This particle gets lost when we don't need it. All we need is a particle with a known velocity. And now when we have collected particles with known velocity, the third part of that spectrometer is working. We know both particles have the same speed, let's say 5 meters per second. And now in the third region, again, we apply magnetic field. Magnetic field makes them move in circles. However, now, depending on charge and mass, the radius is different for different particles. And this sensor, well, gives us the value of the diameter or radius, and we can apply our equations to calculate the ratio E over M, charge to mass. You're going to do a similar lab, calculating charge ratio, charge to mass for the electron. And if we know the ratio E over M, well, we need to know a charge, for example, to calculate the mass. The charge of electron had been calculated before by Millikan, and this experiment like that, well, basically that's how we weigh particles. It's the last question related to charges traveling in magnetic field. The work done by magnetic field on the proton traveling in magnetic field is not 60. No. You had exactly the same question on a pre-session quiz. So it's a really good question. It happened just a week ago, so, but still, what do we know about work? Everything again. In particular, what was the answer? What did you say? 0. What did you say? Why? All right. In that case, you might be one of those students who wrote one of these comments. Well, you left a lot of comments, correct and not so correct, and I have only this space. So the exact answer to this question is simple: 0. Magnetic field doesn't do any work, because if you look at the right-hand rule, force is perpendicular to velocity always. It's just how it works. And when we calculate work, we have to multiply by cosine of 90 degrees. In that situation, cosine of 90 is 0. That's it. Work is 0. So magnetic force doesn't change kinetic energy of a particle. Speed remains the same. But if you had magnetic field can change because there is no force applied, that's not true. The force is applied. It is perpendicular. Or if you say it cannot change magnitude of velocity because travels with constant speed, again, that's not specific enough. When you answer a question, you have to be very specific. In this situation, there is no work only because the angle is 90 degrees between velocity and force.